In this video, we will be answering a worksheet on radioactivity. The lesson is connected to the topic on atoms, the values, how to compute for atomic number, atomic mass, um, the relevance of protons, neutrons, and other relevant particles that comprise the simple atom. So, yeah. We have to first ask ourselves what an atom is. It's everything. Everything is made of matter. Matter is made of atoms. Um, this particular concept is being taught in um, particular fields from physicists, astronomers, chemists, and cosmologists. You do have to know that um, the atomic mass is equal to basically the nucleus. Since proton and neutron, uh, these green particles in this illustration mean the protons, while the these blue particles comprise the neutron. So they basically make up the nucleus, and these violet particles are the electrons. Obviously, by the minus sign, you could already see that it's a neutron since these particles are negatively charged. They have no mass. Yeah, they are negatively charged. It's basically the perfect opposite of protons, particles that are positively charged. So, with that in mind, we now know that the atomic mass is equal to basically everything, all the particles that we have in the nucleus of an atom, proton plus neutron. The atomic number is equal to proton if the element is an ion. Since the atomic number would always be equal to proton if the element is an ion, such that you might want to recall the definition of what an ion is. An ion is defined by an atom that doesn't have a balanced ratio on the number of protons and protons and electrons. They're not balanced. So this is equivalent to an ion. If there are more protons than electrons in an atom, it's called a cation. While the opposite, such that electrons are more than the number of protons, the ion would be considered specifically an anion. So that's it. If the atomic number if the atom is, or the element is a neutron, or if it's neutral, actually, not neutron, I'm sorry. If the element is neutral, that means, in other words, the proton is equal to the number of electrons. That means, the element is neutral. And the atomic number in that sense is equal to the proton, which is also equal to the neutron. That's all. Radioactivity deals with emission of energetic particles of an atom. Unstable elements usually tend to have what we call radioactive eating. And if the ratio of protons and neutrons are not equal, the element becomes unstable. So I stated earlier that an element is an ion if the ratio of protons to electrons are not equal to each other. In this sentence, this one, the ratio of protons and neutrons, if they're not equal, the element becomes an unstable element. This process of decay happens until the atom's neutron makes its atom stable. So, there are three types of radiation. First would be called the alpha particles. Second would be called the beta particles, and third would be the gamma rays. So imagine that this is an illustration of the radioactive atom, and in it are particles. Um, I don't exactly recall the entire definition from this illustration. However, um, this is directly copied from my teacher's lecture, our chemistry teacher's lecture. So, for nuclear reaction, it mainly happens in the nucleus, hence the adjective nuclear. So, I won't be explaining much on fusion and fission, but it's important to know them as relevant with the term nuclear reaction. So we have here the usual illustration of an element in the periodic table. Um, of course, this x variable would be the element. The A would be the atomic mass, while the subscript Z would be the number of protons, or in other words, the atomic number. So you also might want to know this useful piece of information. C stands for carbon, Ca stands for calcium. Now, for I'll be explaining actually five types of radioactivity, if I'm not wrong. There isn't a specific title on this table, but if this table is pretty relatable to what you're studying right now in grade 11 chemistry, uh, it's pretty good actually. Let's start with the first one, alpha decay. It's defined by the loss of an alpha particle. The type or the illustration would be this. It's basically the A would stand for the alpha particle, and of course it has 4 as the atomic mass, and the atomic number would be 2. In the periodic table, in real time, this could also be translated as helium. It has an actual atomic mass of 4 and an atomic number of 2. Hence, this one. Alpha decay has the lowest penetration strength, and it has consequently the highest ionization power. You could already include, based on these definitions, penetration strength and ionization power. They are inverses of each other. That would be applicable to the definition of gamma ray. Gamma ray basically has the opposite of what gamma decay offers. Gamma decay is basically the opposite of alpha decay in the sense that if alpha decay has the lowest penetration strength, gamma decay would have the highest number of penetrative strength. And the alpha decay would have the highest ionization power. The gamma decay would have the lowest. So that's it. For beta decay, of course, in the Greek alphabet, this symbol is beta, literally beta. Nothing more, nothing less to say about that. It's the loss of a beta particle. The mass is negligible since, as you can see here, the atomic mass is 0. So this is the beta particle. Loss of one particle in the atomic number. For example, given that you have carbon that has an atomic mass of 14 and an atomic number of 6, it turns into nitrogen such that the atomic mass is still the same, but then the atomic number increased by 1. So coming from nitrogen back to carbon, that occurrence or dilemma happens in real time if a beta particle intervenes to it. So basically 7 minus 1 is 6, right? So that's it. That's all that you need to know. It's pretty basic logic, but it's going to be pretty challenging to digest in the context of this lesson on radioactivity. So I stated earlier that the gamma decay is pretty opposite with the alpha decay in terms of the number of penetration and high and ionization power. Um, the main definition for gamma decay is that it has no mass. It's definitely not a particle, so it has no effect on the nucleus. I stated earlier that electrons don't have any value. Um, they're just basically electrons. They make an atom negatively charged. They make it an ion if the number of electrons uh, become more than the number of protons. But then, in this context, for gamma decay, it's basically written as this one. So the Y value, the Y symbol in the Greek alphabet would stand for gamma, and there would be 0 at the atomic number, 0 at the atomic mass. Another fun fact though is that for gamma decay, one of its one specific element, cobalt 60, it's used as treatment for cancer. If I'm not mistaken, it's one of the chemo drugs that are used in hospitals right now. So yeah. For example, given this, if I'm not mistaken, letter U in the periodic table is called uranium. Given that we have a gamma ray, a gamma decay that would happen, what is the product? If these are the reactants, what would be the product? Of course, it would be the same. Nothing would change. That's basically the nature of gamma decay. Nothing happens at all. There is no effect on the nucleus. There is no effect on what constitutes the atomic mass, which is basically proton plus electron. I'm sorry, proton plus neutron, and what constitutes the atomic number, which in the context of an atom that is not an ion, the proton isn't affected in any way. A proton is still logically part of a nucleus. So, in the second example, as you can see here, actually I've already written the answer. It's still gamma decay, since nothing really changed. It's still thorium. TH stands for thorium, if I'm not wrong. Anyways, let's move on. Positron emission. What we have to know in this is that we have an electron that has an atomic mass of 0 and an atomic number of 1, positive 1. So basically, you convert a proton into a proton that's located in a nucleus, as always. Turn it into a neutron. So, for example, as you can see here, we have oxygen, atomic number of 8, atomic mass of 15. It turns into nitrogen, whose atomic number is 7, and the atomic mass is 15. If you put a positron emission, this is actually the perfect reactant that makes the product what it actually is. Since 7 plus 1 is 8, 15 plus 0 is still 15. So, yeah. This is an example. This example is basically an oxygen undergoing proton emission. So, theoretically, wait, I'll just mention about this that I was about to say later. For electron capture, it's basically the drawing of an electron into an atom's nucleus. We have this illustration. Electron, the atomic mass would not change at all. I mean, yeah, it would not change at all. And the atomic number would be -1. The emitted energy is in the form of X-ray. So in this example, apologize. I'm not really that I haven't really memorized much elements in the periodic table. So let's just say this is Hg, and given we have an electron capture particle, um, the atomic mass would still be 201. However, the atomic number would change. 80 minus 1 would be 79. The atomic number of 79 corresponds to Au, or aurum. I think that's the old word for gold. I'm not sure. Anyways, and now I'm about to say what I initially wanted to say earlier. Electron capture is, in theory, the same as beta decay. As you can see here, hang on, we just copy paste the model for electron capture. As you can see here, there is no change in the atomic mass, but there is a -1 for the atomic number. They have the same illustration, the same models. What makes it different, according to my teacher in chemistry, is that for beta decay, usually this symbol is located in the reactant side part of the equation. What I mean by equation is this kind of thing. Usually you have an element here plus the type, the radioactive particle, and the product. Basically, these are the reactants. This kind of equation is more relevant in the context of the keywords absorbs. And I'll show you another equation that corresponds to the keyword decays. Basically, we have the product here, then the reactant, or the element, initial element, plus the radioactive particle that made, together with the element, what the product is. So yeah, that's basically the difference between beta decay and electron capture. For beta, the symbol is located in the reactant side of an equation. For electron capture, it's usually in the product side of the equation. That might be quite unclear in a way, but even in that sense, I don't think there's any much restriction. Beta decay, electron capture, they're basically the same, if not same in all aspects. So this is basically the summary of everything I showed you earlier. For alpha decay, for the atomic mass, that would be the letter A, and the Z would be the atomic number. Decrease by 4, decrease by 2 in this context. For beta decay, the atomic mass remains unchanged. The atomic number would increase by 1 in this context, in the context of this expression. For gamma decay, the atomic mass still remains unchanged, as well as the atomic number. It's pretty easy to remember gamma decay. You can associate it with both the atomic number and mass being unchanged. For positron emission, it's basically the opposite of beta decay and electron capture. Since you know that the electron capture is the same as beta decay in a certain way, you could say that positron emission is the opposite of both of them. So for positron emission, the atomic mass remains unchanged, and the atomic number would decrease by 1. in the context of this expression. So I think we could make one specific conclusion from this table. Out of the 5, one of them has or contributes to a change in the atomic mass. That would be the alpha decay. The rest, the atomic mass would remain unchanged, as you can see here. That goes for beta decay, gamma, positron emission, and electron capture. But as for alpha decay, there is a change in the atomic mass. Also, there's also a few more things that you have to know. This is what I basically showed you earlier. I asked my teacher about if these were correct. He said it was. They were correct in a more sensible way. But I'll talk about it more later. For the proton, it's basically equal to 1 atomic mass and 1 atomic number. Since the proton is actually equal to the amount of atomic number, the amount in atomic numbers. And it is one of the building blocks that constitutes an atomic mass. Hence, this illustration could also be called as hydrogen, since in real time in the periodic table, hydrogen has 1 atomic mass and 1 atomic number, while the neutron has no change in the atomic number, since the atomic number is equal to protons and is equal to electrons in the context that the atom is not an ion, right? So for neutron, it doesn't play any part in defining the value of the atomic number. It plays a value in defining the number of atomic mass, since the atomic mass is equal to neutron plus proton, basically all the particles that are in the nucleus. So let's start with this. For decays, the keyword decay, the new element would, or the product would have an arrow here. There would be an arrow here, and the type of radioactive decay, whether it's alpha or beta or positron emission or gamma decay, any of these, and you add it with the initial element, the reactant. So that goes for decays. As for absorbs, we have the reactant element here, which is added together with the type of radioactive decay. So it's either we put alpha decay, beta decay, or in other words, electron capture, gamma decay, or positron emission. Then we put the product here, the final element or the result from these two reactants. So yeah, let's start doing sample problems. It's pretty long, as you can see here. I'm thinking of making a part 2 for this video, but for now, let's answer as much as we can while not making the video too long as much as possible. Start with number 1. So given we have AR, I am assuming that, I hope I'm not wrong, the element is called argon, and it absorbs a beta particle. As you can see here, reactant plus the particle is equal to the product. This is the system for absorbs, as you can see here. So, sorry, the atomic mass is 37. So nothing changed. 37 plus 0 is still 37. 18 minus 1 would be 17. I hope you have your periodic tables with you. You might need it. You need to find the specific element that corresponds to a specific atomic number. So in this case, 17 is Ci or Cl. I'm sorry. This is chlorine, if I'm not mistaken. This is the answer for number 1. For number 2, as you can see here, 251 became 247. Of course, based on what we're seeing right now, we have something like this. This is decay. An element is the element over here is decaying. So 251 minus 247, that would be 4. And 98 minus 96 would be 2. This is an alpha particle. This is the final answer. The element is undergoing alpha decay to become this. But for some reason, the element did not change. The name of the element itself did not change. Weird observation. Right, let's move to number 3. By the way, I have to write here alpha decay. For number 1, it's beta decay. For number 3, we have here beta decay, actually. Or electron capture. Choosing from the two of them, hang on, I need a few seconds. I'll just recall what my teacher said about the definite difference between between beta decay and electron capture. Alright, I think I can see now. The element is for this nuclear reaction, it's actually beta decay, not electron capture, for the reason that this symbol is at the product side of the nuclear equation or reaction. If it's electron capture, this symbol should be at the left side, probably in absorbed nuclear reaction scenarios. But for number 3, 42, it's still 42. 42 minus 0 is still 42. 19 minus 1. Let's say 19 plus 1 would be 20. Because 20 minus 1 would be 19. That's how we do arithmetic in this lesson. It's pretty eerie or odd in a certain way, but you'll get used to it one day. It's pretty easy to get used to it. So this is calcium. That's the final answer. For number 4, francium 212 decays by alpha emission. So we have the keyword decay, so the equation would be something like this, such that francium is located here. By the way, if this is the name of the element and whatever number is written beside it, separated by a dash, would be the atomic mass. So in the periodic table, the francium is 87, and so if we put alpha emission or alpha decay, the symbol would be like this, right? And 212, what's the number that if we add with number 4, I'm sorry, let me reword it. Adding the number 4 with which quantity, what number would result to it to get 212? It's basically 208, since 208 plus 4 is 212. 85 plus 2 is 87. 85, atomic number of 85 at the periodic table would be AT, or astatine, if I'm not mistaken. So let's say, this is a bonus question, by the way. Let's say that, I'm sorry, instead of decay, it's absorbs. The nuclear equation template would look like this, in the sense that francium would be here, same 212 atomic mass, 87 atomic number, and like this we get gold, or Au, aurum. I hope you can ponder the difference between them. If francium decays by alpha emission, this is what we get. If the same francium element absorbs by alpha emission, this is what you get. Right. For number 5, phosphorus 32 decays by beta emission. So let's write here phosphorus. Atomic number is 15. Atomic mass is 32. Decay, so the template would look like this, such that the beta decay or emission particle would be located here, and the result, or the missing value, would be this. I think this is sulfur by the abbreviation S. This is sulfur. Right. For number 6, fluorine 18. I'm not sure if it's supposed to be FL or F. I'm not sure. Anyways, decays by positron emission. The symbol for positron emission is like this one. So we write here the symbol for positron emission. And what do we get? 18 plus 0 is still 18. 9 minus 1 is 8. 8 plus 1 is 9. That's how we check. So an element of atomic number of 8 is oxygen. This is the final answer. Actually, what I'm boxing right now, the elements that I box, they're actually not final answers, but what matters is that you've completed the nuclear reaction or equation. Right. For number 7, krypton 76 absorbs a beta particle. So the keyword is absorbs. Beta particle, we get something like this. So krypton, Kr, atomic mass 76, atomic number is 36. So absorbs, because the word problem says the element absorbs a specific particle, it would look like this, such that beta particle would be put here, and the result would be 76, 37, I'm sorry, 35. 35, atomic number would be Br, or bromine, if I'm not wrong, in terms of saying how you're supposed to say the element and what that element actually is, coming based from the abbreviation. Let's move on to number 8. Aluminum 27. Aluminum has an atomic number of 13 and absorbs. So we have a chassis like this. Alpha particle would be written as this. And what's the result? 27 plus 4 is 31. Atomic mass of 31. Atomic number of 15. 15 atomic number is nitrogen in the periodic table. Right, let's proceed to number 9. Nitrogen 14. The atomic mass is 14. Atomic number would be 7. Absorbs an alpha particle and emits a proton. So this, we actually have two particles going on in this scenario. First, the element nitrogen 14 absorbs an alpha particle and emits a proton. So first, let's just write actually wait, hang on, because this is how we write it usually. Since the proton is written as like this and the alpha particle is written like this, we put the proton here, and this is the missing value. So given 14 plus 4, that would be 18. Of course, the atomic mass altogether should be 18, and for the atomic number, it should be 9. But given that it also emits a proton, the element won't be based on these values. So obviously, we subtract both the atomic mass and atomic number by 1. So we get 17 and 8. That would be oxygen. So that's an equation. Okay. This is a proton, alpha particle will be that. Let's move on to this is another worksheet on radioactivity. I found this randomly from the internet. I don't own this. I acknowledge that it's the property of the person who made this. And yeah, let's actually try finishing this in the next video. Thanks for watching. I hope you learned something today. I'll continue the next video shortly after this.